Hey guys, not really sure what happened there. Wait for everybody to get back on the new stream. Not really sure what happened. Just kind of shut down randomly. Just had to restart, put a new stream up. Make sure everybody's here before we keep going. That was a little crazy. So basically what we can do here is just kind of ignore the whole left half of this graph before x equals 0. Just kind of ignore everything to the left of the y-axis. And we start out right here. We have some initial velocity that takes us down, but then our restoring force catches us and it pulls us back up, and then we pass equilibrium on the way back up, and then we go up to some point, and then we get pulled back down by our force due to gravity and our restoring force pushing us away from where we're going. So it's just a constant up and down motion. So that's the first example. That's just basically unrestricted motion. If you're pulling the spring, you let it go, then it's just some unrestricted motion, just keeps going up and down forever. So let's look at the second example, example number 2. It says an object weighing 32 pounds stretches a spring 2 feet. It is pulled down 6 inches and released in a medium where the resistance is 4 times the velocity. Find the expression that models the behavior of the mass displacement from equilibrium. So here we've got mg equals 32. So that tells us m equals 1 slug. B here is 4 times the velocity. And it is pulled down 6 inches. Oh no, it stretches the spring 2 feet, so L equals 2 feet. So mg equals KL tells me that 32 equals 2K, so K equals 16. And then the initial displacement U of 0 is 6 inches, which I have to convert to feet, so everything is consistent. And it's pulled down and released, so it doesn't get any initial velocity, so U prime of 0 is 0. So that means our initial value problem is going to be, let's see, U double prime plus 4U plus 16, or 4U prime plus 16U equals 0. And U of 0 equals 1/2 U prime of 0 equals 0. So this is our initial value problem that we need to solve now. So, solution. Again, just constant coefficients. We go straight to m squared plus 4m plus 16 equals 0. And see what happens. This is going to equal, or what are we going to get? We're going to get m, let's see, can we factor that? Just try the quadratic formula. m12 equals -4 plus or minus square root of 16 minus 64 all over 2. So the two roots here will be -4 plus or minus the square root. Let's see, I can factor out a 16. I get 4 square root of 1 minus 4 all over 2. So we get a m12 equals -2 plus or minus 2 I square roots of 3. So alpha is -2, beta is 2 square roots of 3. So u of t is going to be c1 e to the -2t cosine 2 square roots of 3t plus c2 e to the -2t sine of 2 square roots of 3t. So that's our homogeneous solution if we have complex roots, and here we have alpha is -2 and beta is 2 square roots of 3. So then, using the initial conditions, u of 0 equals 1/2. That's going to equal c1 e to the 0 cosine of 0 plus c2 e to the 0 sine of 0. That basically tells me c1 is 1/2. And some more work, u prime of 0 equals 0. That tells us that c2, I believe, is going to be 1/2 square roots of 3. So our position, displacement as a function of time, is going to be 1/2 e to the -2t cosine 2 square roots of 3t plus 1/2 square roots of 3 e to the -2t sine 2 square roots of 3t. And if we plot that one, see what happens. So let's plot this function. So 1/2 e to the -2t cosine 2 square roots of 3t plus 1/2 square roots of 3 e to the -2t sine 2 square roots of 3t. And we'll graph that. And we have some damping. Again, only look at everything to the right of the y-axis. We have some dampening going on. We go down, we pass equilibrium, but then we come back up and we kind of very slowly reach equilibrium, kind of like you would expect if the spring were damped. So then, in an exaggerated sense, this is what our graph would look like. So an exaggerated, very exaggerated. This is what we call an underdamped system. So it's damped, but it's not like going straight to the equilibrium position. It's kind of oscillating above and below the equilibrium position. So it's an underdamped system. All right, let's look at the next problem, example 3. It says the same thing except the air resistance is 8 times the velocity. So in this case, B is 8 and everything else is the same. So it's going to be u double prime plus 8u prime plus, I think it was 16u equals 0. U of 0 is 1/2. U prime of 0 is 0. So pretty much the same thing, except the air resistance factor changes. That's just going to change how it damps the system. So the solution is going to be m squared plus 8m plus 16 equals 0. And that's m plus 4 quantity squared equals 0. M equals -4 is repeated. So it's a repeated root. So what's going to happen is we're going to have u of t is equal to C1 e to the negative 4t plus C2 times t e to the negative 4t. And using our initial conditions, so using initial conditions, we get C1 is 1/2 and C2 is 2. So then U of t is 1/2 e to the negative 4t plus 2t e to the negative 4t. And let's graph that one just to see what it looks like. That's 1/2 e to the negative 4t plus 2t e to the negative 4t. And I want to do t is greater than 0. So it kind of starts out and then slowly approaches equilibrium and maybe oscillates one time above equilibrium. So this graph kind of looks like this. This is what we call critically damped. Critically damped. So when you have a repeated root, that's how you know you're critically damped. Underdamped, complex roots. Critically damped, repeated roots. Number 4, it says just change the air resistance to 10 times the velocity. So number 4, B is equal to 10. So then our differential equation is U double prime plus 10U prime plus 16U equals 0. U of 0 still 1/2. U prime of 0 still 0. Solution is going to be, let's see, m squared plus 10m plus 16 equals 0. And we should factor that as m plus 2 plus 8. m1 equals negative 2. m2 equals negative 8. And so U of t can be C1 e to the negative 2t plus C2 e to the negative 8t. And initial conditions tell us that C1 turns out to be 2/3 and C2 turns out to be negative 1/6. And this graph is what we call, or this function, this system is what we call overdamped. So this is 2/3 e to the negative 2t plus or minus 1/6 e to the negative 8t. This is what we call an overdamped system. Let's see, negative? Maybe positive 1/6. T equals 0. Two-thirds plus 1/6 would be too much, right? Let me work out these coefficients really fast. So it is going to be more or less like that graph right there. But let me work out these coefficients. So U of 0 equals 1/2 equals C1 plus C2. U prime of t is going to be negative 2C1 minus 8C2. And U prime of 0 is going to be 0, which is negative 2C1 minus 8C2. So we got two equations, C1 plus C2 equals 1/2, and negative 2C1 minus 8C2 equals 0. So what can we say? see if I multiply this by 2 and add them together, get negative 6 C2 equals 1. So C2 equals negative 1/6. Yeah, that's right. And then C1 equals 1/2 minus or plus 1/6, which is 2/3, right? And for some reason that graph just didn't look right to me, because the displacement should start at a positive value. So 2/3 minus 1/6 e to the negative 8t. Oh yeah, that's because it's starting at negative t values in this picture up here. So graph for t greater than 0. Well, I'll just write it out. So the graph should look like this. And it just strongly approaches equilibrium position. Because there's so much dampening, we call this overdamped. So the takeaways are, if you have complex roots, it could either be undamped or underdamped. So undamped would just mean b is equal to 0. If you have a repeated root, then it's what we call critically damped. And if you have distinct real roots, it's what we call overdamped. It's like the spring barely moves and it slowly approaches equilibrium. So that's overdamped. Now, example 5 says a 16-pound weight stretches a spring 32 inches. So mg is 16, L is 32 inches, which is really 32/12 feet. And that can reduce to like, what is that, 16/6. Divide by 4, 8/3 feet. It is released 2 feet below equilibrium position in a medium having a damping force equal to half the velocity. So b is 1/2. U of 0, it says, is 2 feet. And if it's pulled down and released, then it has no initial velocity. And it has some external force described by f of t equals 10 cosine t. So f of t equals 10 cosine t pounds, or 3t pounds. Okay. And so let's look at mg equals kl. So that's 16 equals 8/3 k. And so let's see, divide by 2, multiply by 3 is 6. So k equals 6. So our differential equation what's m? M is 16 over 32, which is 1/2 a slug. So our differential equation, our initial value problem, is 1/2 u double prime plus 1/2 u prime plus 6u equals 10 cosine 3t. U of 0 is 2. U prime of 0 is 0. So this is our problem. It's a non-homogeneous equation. It's a non-homogeneous equation. And I'll just probably use a method of undetermined coefficients to solve it. So first, find a homogeneous solution. And that's 1/2 m squared plus 1/2 m plus 6 equals 0. And I'll rewrite that as m squared plus m plus 12 equals 0. And those roots are really nasty. M1 to turn out to be -1/2 plus or minus I times square root of 47 over 2. So alpha is -1/2, beta is square root of 47 over 2. So UH of t is going to be C1 e to the negative t over 2 cosine square root of 47 over 2t plus C2 e to the negative t over 2 sine square root of 47 over 2t. So that's our homogeneous solution. And now we guess UP of t is some constant a times cosine of 3t plus some constant b times sine of 3t. UP prime is going to be -3a sine 3t plus 3b cosine 3t. UP double prime be -9a cosine 3t minus 9b sine 3t. And this is all to do method of undetermined coefficients. Substitute that into the non-homogeneous equation. Get -9a cosine 3t minus 9b sine 3t plus -3a sine 3t plus 3b cosine 3t plus 12 times a cosine 3t plus b sine 3t all equals 20. If we multiplied by 2 all the way through, that 2 would multiply by the 10 and give us 20 cosine 3t. And from there, we find out, eventually do all the work, find out that a is 10/3 and b is also 10/3. So u of t is actually C1 e to the negative t over 2 cosine square root of 47 over 2t plus C2 e to the negative t over 2 sine square root of 47 over 2t plus 10/3 cosine 3t plus 10/3 sine 3t. Now we can use our initial conditions to solve for C1 and C2. So now use your initial conditions to solve for C1 and C2. After some more differentiation and all that stuff, you get C1 equals -4/3 and C2 equals -64/3 square root of 47. So the unique solution, u of t, is equal to, I'm going to factor out that e to the -t/2, gives me -4/3 cosine square root of 47/2 times t minus 64/3 square root of 47 sine square root of 47/2t plus 10/3. I'll factor that out. And that leaves cosine 3t plus sine 3t. And that's our unique solution. And notice we have a transient term. So this first half is a transient term. And this is what we call our steady state term. This is transient because the exponential goes to 0. So eventually, even though it starts out oscillating and does whatever, it'll just eventually turn into this shifted sine wave right here. So it starts out oscillating and does whatever at the beginning, but then at the steady state in the long term, it just approaches this 10/3 cosine 3t plus sine 3t shifted sine wave. So that is eventually the overall solution. If we graph it, we'll see that behavior. So let's look at the graph. See if we can get that to kind of show. So it's e to the -t/2 times -4/3 cosine square root of 47/2t minus 64/3 square roots 47 sine of this thing plus 10/3 times cosine 3t plus sine 3t. And I'll look at it for t greater than 0. So you can kind of see this graph down here. It starts off by doing some weird oscillation stuff, but then eventually the steady state term takes over and it just does a normal sine wave oscillation. So initially that's where the instability is, but then the steady state kicks in eventually and takes over the whole system. So that forcing function is really just eventually going to take over the whole system and tell it what to do. The last one is similar, except just slightly different parameters and all that stuff, a different forcing function, but example 6 says the mg is 12, so m is 12/32 slugs. stretches the spring 6 inches, so L is 1/2 a foot. And 12 equals 1/2 times K, so K is 24. No damping, so B is 0. It started at equilibrium, so U of 0 is 0 and U prime of 0 is 0. So it starts motion at equilibrium. Starts motion at equilibrium. So then the difference equation to solve initial value problem is going to be, let's see, 12 over 32 is divided by 4 is 3 over 8. So 3 over 8 U double prime plus 0 U prime plus 24 U equals cosine 8t. So if we multiply through by 8/3, we get U double prime plus 64 U equals 8/3 cosine 8t. And we'll solve the homogeneous equation U double prime plus 64 U. Oh, that's not U. Yeah, it is. Equals 0, which tells me m squared plus 64 equals 0. So m equals plus or minus 8i. So UH of t is C1 cosine 8t plus C2 sine 8t. Initial conditions tell us that C1 is 0 and C2 is equal to, oh, can't use initial conditions yet, can we? We have to find the particular solution first. So UP, I guess, UP of t equals, normally we just guess A cosine 8t plus B sine 8t, but that duplicates y or UH. So we have to multiply by t. So we say A t cosine 8t plus B t sine 8t. Do all the work. Turns out A is 0, B is 1 over 6. So the solution U of t is going to be C1 cosine 8t plus C2 sine 8t plus 1 over 6t sine 8t. And this last term is what we call resonance. Means the natural frequency of the system is in a line with the frequency of the forcing motion, which means it's just going to grow. The solution's going to grow over time. So it starts out oscillating, but then it gets bigger, basically like a straight line. So this is what we call resonance. And this is a bad thing, especially if you're like building a bridge and there's a bridge that was actually a fatality of this resonance effect. And it was called the galloping Gertie. Galloping, let's see, I think it was GIRDY or GURDY. Or actually GIRTIE maybe? Galloping Gertie. But it was like a bridge that was built, and the wind, that was basically like the forcing function, was in line with the natural frequency of the bridge, and the bridge just started to basically like erupt and just came crashing down. So it was a problem. So just I think you can Google that, make sure. Can't remember if I spelled it right or not. Galloping Gertie or Gertie. GERTIE. There we go. GERTIE. TIE. So, yeah, it was a suspension bridge, and the wind picked up one day and came in at the same frequency. So it started creating oscillations that were the same frequency of the natural motion of the bridge. And it produced disastrous results. The bridge came tumbling down. So anyway, yeah, that's it for today. Sorry, I don't know what happened at the middle there with the stream, but yeah, I think we're good to go now. Any questions, hit me up, you know, over the weekend. I'll be available a little bit. So have a good extended weekend. I'll see you guys next week. Have a good one.